Here we go. So we'll probably just cut the true or false questions. Maybe we'll do those on Slack offline, and that'll save the 15 minutes that we went over on the quiz. OK, a point that came up in lab yesterday, which is definitely worth making, is that there's this terminology issue between the number of layers and the number of hidden layers, which are not the same thing. So this picture here that we looked at last time, I would say it has one hidden layer, but I would say it has two layers. Because I'm defining the number of layers as the number of times you do this transformation where you multiply by a matrix, add the biases, and apply the activation function. So to go from the first column to the second column, I'm calling that a layer. And that has its parameters associated with it. And then to go from the second to the third, I'm calling that a layer. So in general, the number of layers is one more than the number of hidden layers. And just watch out for that, because that can be super confusing. There might even be some extreme people who would call this 3 layers. But I don't think most people would do that. I think the most standard thing is this would be called 2 layers and 1 hidden layer. OK, yeah. Good. OK, so Softmax. This was obviously coming up a bunch in lab on Monday and yesterday because you needed it for the lab. So let's finally talk about it. So when we use neural nets for classification, now we take advantage of the fact that that last layer does not just have to have 1 unit in it. So when you're doing regression, the last layer just has 1 unit, meaning you're just getting a number out, like exercise 0 in the lab, and then that number is your prediction. But when you're using neural networks for classification, for example, in the lab, there are 10 classes for the digits data set. You actually have 10 outputs. And what those 10 outputs are there the 10 probabilities for the 10 classes. So probability that's a 0, probability that's 1, probability that's a 2. And the softmax is a special activation function that you use on the last layer when you're doing classification. And is different from all the other activation functions because it isn't individually applied to each unit. So all the things we talked about, I said they were element-wise. You do it to this one, you do it to this one. The softmax is special in that you have to look at the whole vector coming out of 10 things, and you do something to the vector as a whole. And this is the actual function itself, but let me tell you how I suggest that you think about it. You have 10 numbers coming out of this crazy neural network, and they're supposed to be probabilities. What do we know about probabilities? They need to be non-negative, and they can't be more than 1. These are discrete probabilities. Remember, it's not a density function. So here's how I think about this. I have these numbers. I want them to be probabilities. OK, let me first make sure they're non-negative. How can I make sure they're non-negative? Well, let me just take exp of all of them. Exp of something can never be negative. OK, great. Now I turned all my numbers possibly negative into numbers definitely not negative by taking exp of them. But now I have the other problem that they might not add up to 1. OK, let me just add them all up, divide by the sum, and now they add up to 1. And that's what this function is. It looks kind of funny, but the numerator, you have, oh, this needs to be an I here. In the numerator, you have exp of the number, but in the denominator, you have the sum of all the exps of all the numbers. So for example, if my vector coming out was 2, 3, 5, then I'd get e to the 2, e to the 3, e to the 5. But then I needed them to add up to 1, so I would divide by that sum. So I would get e to the 2 over e to the 2 plus e to the 3 plus e to the 5, e to the 3 over e to the 2 plus e to the 3 to the 5, e to the 5 over e to the 2 plus e to the 3 plus e to the 5. And then if I added those all up together, I would get e to the 2 plus e to the 3 plus e to the 5 over e to the 2 plus e to the 3 plus e to the 5. And so I would get 1. So they would add up to 1, right?
So the proportions for like 2, 3, and 5, doesn't the proportion change when you take e to not linear. So like,
Well, that's why you're dividing by the versions after you've taken S. You can't just divide by the original numbers. But you're dividing by these. So at the end of the day, you have this, this, and this. You add them up. It's going to be 1. Because the 3 numerators are going to add up to the same thing as the denominator. So yes, their proportionality changes, but that's fine. They're not negative. They add up to 1. We're happy.
first, the top one is still the top one.
Yes, and it's monotonic. The top one is still the biggest. The second one is still the second biggest. The order stays the same, tiny.
And what I think Brian was saying is that the proportion changes because it's a nonlinear transform.
It's true that the proportion changes, but we don't really care that much about the proportion at the beginning. We just want something that could be a probability. We're going to define a loss that looks at those probabilities. We'll try to minimize the loss, and it'll all kind of work itself out. Tom?
Do we have to worry about overflow with this?
Do we have to worry about overflow? Yes, and I will get to that in a second.
Thank you.
Okay. Yeah, so why is it actually called the softmax, in case you're wondering? It's because it is like the max function, except more soft, and I will show you a demo of that. Okay, ignore this for a minute. Okay, so here's the softmax function I just described to you. It's e to the z. So this, I'm just using NumPy's vectorized thing. So that x to the z that I highlighted is doing it for the whole vector. And that whole vector is getting divided by this denominator, which is just a single number. And so I get the whole vector out at once. So here's just a z I made up. And what's the max of it? Well, the max of it is 7. The biggest number in my list there is 7. So if I one-hot encode that, then this is what the max is. -5 is not the biggest, -1 is not the biggest, 3 is not the biggest, 7 is the biggest, and 5 is not the biggest. So that's kind of a one-hot encoding of which of these numbers is the biggest. And the softmax is actually kind of a soft version of that one-hot encoding of the max. Because look, this number is kind of close to 0, this number is kind of close to 0, this number is kind of close to 0, this number is 0.8, that's pretty big, and this number is kind of close to 0. So it's like a softened version of that idea. So whichever number is the biggest, its softmax is also going to be the biggest. We just talked about that. It's monotonic. You preserve the order. And if we think of this one-hot encoded version of the max as the max function, it's doing something similar to that. And in fact, so first I'll just show you that they add up to 1. I mean, you probably believe me that they add up to 1, but here you go. They add up to 1. But look at this one. This is a case where I changed a 7 to a 100. So there's one that's really a lot bigger than the others. Well, what's going to happen when you take e to the power of 100? It's going to totally be way bigger than all the other things. And so you're going to have e to the 100 over e to the 100 plus some tiny stuff. That'll just be slightly less than 1. And the other ones will be like e to the 2 over e to the 100, and that'll be really close to 0. And so if I call the softmax, I get basically 0, 0, 0, 1, 0. So when there's one that's like way bigger than the others, it's basically doing the max. But then it's the softer version, because when there's like closer to a tie, you get these probabilities like I'm 40% sure it's this, 40% sure it's that. And so that's where it gets the name softmax. So going back to Tom's question, you had this exercise 5 in lab 2 from a week ago, where you had to notice this log sum x thing and pull out the a and talk about it. And this comes straight out of what we're talking about. So you probably saw in the lab that categorical cross entropy loss that you're supposed to use. It is the loss that takes those probabilities coming out of the softmax and says, hey, try to make the probability of the true thing big and the probability of the wrong things small. So in other words, if this is a classification problem with 5 classes and the real class is 4, then it would be really cool if your model said it's 0% class 1, 0% class 2, 0% class 3, 100% class 4, and 0% class 5. You'd be like, wow, this model is amazing. It is right and so confident. And so that loss tries to get the probabilities towards that, but those probabilities it's never going to be that precise. They're going to come out of your model. This is like the ideal that it's trying to get towards, but it'll really be, 0.1, 0.1, 0.1, 0.6, 0.1, or something like that. Just a minute, Sam. So this is optional, but the full loss actually has this mathematical form. And the point is that it has this log sum x thing in it. And so going back to your question, Tom, yes, you do have to worry about it. And in its loss form, there's actually something you can do about it, which is great. And so this is like the super standard thing that you did last lab. Sam?
Yeah, so just wanted to confirm, the only point where we can go with using Softmax is to get probabilities from the output. Take the absolute value, but no values, and just take the largest one.
Yes, okay, good point. So if you just want the hard prediction, you just want to say, give me your best shot, you don't actually have to apply the softmax. Because whatever was the biggest before, as Ryan pointed out, it's monotonic, is going to be the biggest probability. So you could skip the softmax. But you often do want the probabilities, especially since the loss is a function of the probabilities, not just the hard prediction. And so that's why the softmax needs to be in that pipeline, so that you apply it, get the probabilities, compute the loss, which ends up you take the gradient all the way through that. And so that's why you need it. But yes, good point. OK, so all this is a generalization of logistic regression-y type stuff, but we don't really have time to go into it. So I'm just going to move on to some code. And I managed to fix my TensorFlow installation since last time, hopefully. So you did this one-hot encoding in lab. And it seems that is no longer necessary in more recent versions of Keras. But I think it's kind of nice, actually, because, like, again, think about one of these rows. That row says the digit is a 2, because it's not a 0, it's not a 1, it is a 2, it's not a 3, it's not a 4. And indeed, it is useful for you to think about the loss as it's trying to get the probabilities coming out to look like that row. That would be like the perfect 0 loss situation where the probabilities coming out were 0, 0, 1, 0, 0, 0, 0. And so you could think of the loss as sort of trying to get it to be like that. And so maybe even conceptually, this one-hot encoding of like the ideal probabilities is a useful thing for you to have in your mind. Any questions? OK, so train test split. I know a bunch of you were looking at this code earlier this week in lab. That's great. So I put the softmax at the end. I use this categorical cross entropy, which is the loss that in conjunction with softmax does something reasonable for multi-class classification. That mathematical equation I showed earlier that I said was optional. So I can fit the thing, and I can predict. And when I call predict, what comes out is the probability. So basically 0, 0.9, tiny, 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 tiny. So this thing is pretty confident. It's 98.8% sure that that digit is a 1. And so you could like reverse engineer it and figure out what those numbers originally were. But after going through the softmax, these are the probabilities. And they add up to 1. And the argmax is 1, so that it's saying the digit is a 1. And to Sam's point, the argmax, even before you applied the softmax, would have been 1 as well. That was the biggest thing coming out, and it was also the biggest probability. Questions, comments? Brock.
Yeah, just regarding the Keras input dimension, why not just Keras just hard code that for us instead?
Yeah. There's a lab question that asks exactly that, so you will need to think about it. Yes, I think it's 3D or I don't know, something. You'll get there. Okay, so that's fine. We talked about that. Model.evaluate. Okay, right. So so model.evaluate, because I put this in my compile, I told it to keep track of the accuracy. And so then later when I called model.evaluate, I could print out the accuracy. And now the moment at least some of you, I hope, have been waiting for, I was getting a lot of questions in lab the last 2 days about why is there loss in accuracy? Why are there two things? So let's talk about that. Okay, accuracy is kind of the human one. That's the thing we can relate to. I got 98% of them correct. I got 99% of them correct. I got 2% of them wrong, right? But we cannot directly maximize the accuracy, or in other words, minimize the error rate, because it is not differentiable. And that may sound very abstract, but let me try to make it concrete for you. Think about what are derivatives and gradients. They're about, you change the parameters a tiny, tiny amount in a certain direction, how much does the loss change? That's basically what all this derivative stuff is about. Now imagine you have your neural network and you change the weights a tiny, 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 tiny amount. Then whichever, you're going to get tiny, tiny changes in all those probabilities. But the one that was the best is probably still going to be the best just because your change was so tiny. Your change was too small to change who the winner was. And so all your predictions, which are actually those argmaxes, which is the biggest probability for example 1, which is the biggest probability for example 2, those are all going to be the same. So you change your weights a tiny bit, but your hard predictions are unchanged. And so your accuracy is unchanged, because your accuracy is just a function of the hard predictions. Computing accuracy, you only need to look at what is your top choice for this picture? What is your top choice for this picture? And so you can't do the gradient stuff to it, because the gradient stuff is all about how do infinitesimal changes in the weights result in infinitesimal changes in the loss. Put another way, the accuracy is basically an integer. I mean, we're dividing it by the total number of examples, but if you have 1,000 examples, the accuracy is going to be, I got 980 of them right, or I got 981 of them right. And so it's not a continuous function that you can take the derivative of. It's an integer function. Questions about that? Well, let me finish, and then I'll take questions. The finishing is that the loss, on the other hand, in contrast to that, is something is differentiable and take the gradient of, because it's a function of the probabilities, not the hard predictions. And so the loss is saying I want the probability of the right answer to be as high as possible, and the probability of the wrong answers to be as small as possible. So now if you teeny, teeny, tiny change the weights, all the probabilities will change just a tiny bit too, and so the loss will change just a tiny bit too, and that's what you want, that continuous relationship between your parameters and your loss, so you can say, what is the derivative? Oh, what is the best direction to go in? Okay, I'll take a step in that direction, the loss will change, et cetera, et cetera. All our calculus that we've been relying on, all our continuous math, comes into play. And so there's kind of the human one, and then the one that you can actually minimize. And you hope that they are kind of related, and that if you minimize the loss really well, you'll get a good accuracy, and you probably will. Because if your probabilities are really great, your predictions will probably be great. Questions or comments? This is kind of a big idea. Tanny.
What if the loss and the accuracy do not change kind of together? Meaning you have, let's say, a small change in one and all of a sudden a huge change in the other.
Yeah, what if you have a small change in one and a huge change in the other? That was the question. It's just very unlikely for that to happen, because to have a small change in the loss, it's like your probabilities just changed a little bit, and it's unlikely that just when changing your probabilities a little bit, what is the best probability is going to be totally different every time, and you have totally different predictions and totally different accuracy. So, you make those plots, I think, in the lab, and you see they kind of go hand in hand. But yeah, in general, you wouldn't really expect them to get super out of whack from each other. Except it gets a little more complicated, because now you've talked about regularization. So you add a giant amount of regularization to your loss. Now suddenly your loss has departed more from training accuracy, because the loss not only cares about the probabilities being good, but it cares about lambda times w squared being small. And now they could be more different from each other. And so we have to sort of keep that in mind. But the whole point of doing that regularization thing is that maybe you're going to get actually better test accuracy. So the whole point of regularization was, let's try to make our loss, our training loss, more reflect test accuracy instead of training accuracy, since test accuracy is the thing we really care about. In the unregularized case, just like the vanilla case, then I expect them to kind of follow each other nicely. But also, you could have a case where you've already gotten 100% accuracy on your training set, but your loss keeps going down and down. Because you can't get better than 100% accuracy, but your probabilities still may be improving to get closer to that 0 and 1 ideal thing. Alistair.
Is there anything we need to think about with the loss if we have like unbalanced classes with our data set? You know, because it might be able to reduce the loss by just predicting everything is the one class, but we're ignoring that class that we're worried about.
Yeah, so it is still a problem, but I don't think it's, I think it's a problem when you look at accuracy or loss, because both of them are kind of a sum over examples. And so all the stuff you talked about, like looking at precision and recall and whatever, like that all comes into play. But I think it would kind of plague the loss and the accuracy similarly. 3.
Is loss function a hyperparameter?
Is the loss function a hyperparameter? Yeah, I mean, sure. If our definition of hyperparameter is like the choices we make as humans, then absolutely. Like, we choose the number of layers, we choose the number of units, we choose whether to use regularization, we choose the loss, sure. But it's just that in this case, there might be like a pretty obvious choice. Like, I'll just do the Softmax categorical cross-entry, that's what almost everyone does, versus the number of units where there isn't really an obvious choice. Should it be 100 or 1,000 or whatever? But sure, if you want. OK, 5-minute break. Let's resume at 11:25. Next thing I want to talk about is we've mentioned earlier in the course, this very high-level view of the 3 decisions you need to make. Decision number 1, what is your model? Is it linear? Is it nonlinear? And for example, how many layers is my neural network? Number 2 is you have to pick your loss. Am I using squared error or absolute value error or something else? Have you talked about robust regression in regression 2 yet? Like Huber loss and stuff? Yeah, so is it that? As another example. And then number 3, how are you going to minimize that loss? We talked about those 3 choices. So for example, with neural networks, one hidden layer of size 10. Now I've picked my model. I've picked the space of possible functions from x to y. Now loss, squared error. OK, now for each of those functions from x to y, I've given a way to score how good is that function. And then number 3, stochastic gradient is going to be my computational workhorse for actually getting to that best one, now that I can define what's better than another. So the fundamental trade-off is mainly a matter of number 1, roughly speaking. Like if I have more layers, more units, that can be more complexity, more overfitting, blah, blah, blah. But the thing about neural networks especially is that we actually muddy the waters, and number 3 starts getting all over this fundamental trade-off thing in a very confusing way. And so let's talk about some things. I am going to store the history of fit, which I saw a bunch of you doing in the lab, and I'm going to provide the validation data to fit. I was happy when a bunch of people came to me in lab and said, hey, this is sketchy. I'm passing the validation data into fit. I'm glad you paused and said, that doesn't sound right. And so, as I told those of you who asked me in lab, we need to trust the people who made TensorFlow that the validation data is only being used for reporting purposes, and it's not actually being looked at for the optimization. So it's only so that every epoch or whatever you can compute the validation error, because otherwise, when fit is done, it did not store its path to get there. And so if you just waited until the end of fit, it would be too late. You wouldn't be able to know what was the validation error after 1 epoch, what was the validation error after 2 epochs, because you kind of lost that that path. Or maybe it's stored in history, but I don't think it is. So we provided the validation data, and actually I have set verbose to 0 here, meaning I don't want it to print anything out. But let me actually, well, I'll let it finish, and then I'll run it again. Too slow. Okay, maybe I won't run it again. So, but if you try taking away verbose, it'll like print stuff out as it's fitting, and you'll be able to see those validation scores. So I think you're supposed to make this type of plot in the lab. I'm also making this type of plot. And what you see is that this is the loss, not the accuracy. Because I passed the validation thing into fit, I could get those validation losses as I went along. And so what I can see is that at some point, I basically just start overfitting. The validation error doesn't go down. Just a minute, Tom. The validation error doesn't go down anymore, but the training error goes down. And so that's this kind of muddying of the waters in terms of the fundamental trade-off, is that actually, it turns out if I do a good job of my optimization, then I might actually overfit more. And an even worse scenario, which is not happening here, but imagine this orange line actually went back up, which could happen in some cases. The crazy thing about that is it means you actually want to do a bad job of solving the optimization problem. Because if you just didn't give it enough time to finish, that would actually be better, because it would overfit less. This makes thinking about what we're doing way harder, because I like to think in terms of those 3 steps and just separate them from each other. But now it's all more of a mess. And so there's this idea of early stopping that says, actually, I'm going to keep monitoring the validation error during my optimization, and if it stops going down, I'm just going to stop. So I'm going to use my validation set during .fit to decide when to terminate, which is something we haven't talked about so far. We've only talked about using the maybe number of epochs or using the magnitude of the gradient. But if it's true that all we care about is our ability to generalize the unseen data, then why not do this, right? Regularization plays into this story too, as we just talked about a minute ago, in that if you have more regularization, maybe you'll overfit less, and maybe one way to describe regularization is try to make the thing you're minimizing more representative of test error rather than just training error. And so if you have a bunch of regularization, then maybe this is not going to happen so bad. Tom?
Just want to confirm that when we're fitting the model and storing it in history, it's saving the scores at each epoch?
I believe so, yeah. That's... Yeah, I guess so, because I told it 40 epochs, and it seems to be plotting 40 things, so sounds right.
Thank you.
Yes, for Khan.
So is this early stopping, like say, also used in other models apart from neural network? Or?
Is early stopping used in models other than neural networks? I guess it could be, although I haven't seen it that much. I mean, neural networks especially are really slow to train, so and especially can overfit a lot, so they have a lot of conditions that would make this appealing. I suppose you could do it somewhere else too. I just haven't seen it as much. And yeah, you may have experienced this yourself in lab 2, because you were playing around with number of iterations and stuff, and you may have saw in lab 2 that when you ran it longer, the training error actually went down more, but the validation error was actually higher. Okay, another thing, there are there's 3 types of plots of things going down, and I really don't want you to confuse them. So there's loss, then there's accuracy, which actually goes up, but if you took error, which is 1 minus accuracy, that would be another thing going down. Those are fine. I think they're similar enough to each other that if you confuse them, I wouldn't even be that upset. But this, I really don't want you to confuse. Is this going to... Okay, it's going to take a while. Questions? 100. Okay, Tiny.
So when you're doing early stopping, every epoch, every few epochs, you'll run a predict on your validation set
Yes.
and register that.
Yes, when you do early stopping, every once in a while you'll run a predict on your validation set and get the score and see how it was compared to last time. Okay, done. So this plot is also something going down. It's also the train curve going down more than the test curve. But this is literally the classic fundamental trade-off plot that you've seen over and over and over again, decision trees, KNN, random forest, whatever, that I'm just changing the hyperparameter that controls the complexity, and this is happening. So those are completely and utterly different plots that look almost identical, right? The one up here is during optimization, just one run of .fit, I'm seeing how my progress is going, and then train goes underneath test, and here I'm plotting loss. Here, or error, or whatever. Here, the y-axis is actually the same here, but this is not one run of fit. This is, each point on here is a totally different .fit with a different model with a different layer size. So please be careful about that. You can see how similar they look. Yes, Derek.
The first plot you have loss, the second one you have error. Why would you want to cut on loss? Because you're not interested in loss, you're interested in error. And
Yeah.
And the error might not be changing.
Okay, great, fine. Yes. So Derek's question is why this loss accuracy distinction. So I could do this. Or maybe I don't even know what they call it. This is not going to be worth doing on the fly. Yes, I could plot accuracy. Probably, what did I overwrite the history object? Oh no. Yeah. Okay. Let me run this again. But to answer your question, Derek, it is very typical to plot loss when making this plot because if everything is working properly, you need to see the training loss going down. So the training loss going down is like the most fundamental thing that needs to be happening during optimization. With gradient descent and a small learning rate, it's really going to happen. With stochastic gradient, it might not even happen. But that's like the bare sanity check of like, hey, I'm doing optimization. This is supposed to happen. Is it happening? And so I think if you plotted accuracy or 1 minus accuracy, it would look kind of the same. But you just want to have like the untransformed raw thing to just see, is the thing that's supposed to be going down, going down.
Okay.
Okay, next hyperparameters. So yeah, I can't really talk about all these hyperparameters, but I can at least say there's a lot of them. And we talked a bit about this before. So number of layers. Then each layer you need to choose dimensionality, by which I mean number of units, activation function, regularization, millions different types of regularization that you may have seen in the Keras documentation, L2, L1, dropout, blah, blah, blah. So you can go read about all those types of things. Then you have optimization hyperparameters, which is, for example, how do you initialize your learning rate, momentum, which is something we're not covering in this class, but you can read about, which is like a variant of these algorithms that it kind of tends to keep going the same way it was going in parameter space and won't make such sharp turns. So yeah, back to those like 3 big ideas. Choose your model, choose your loss, choose your optimization algorithm. Each of those 3 things has hyperparameters, right? The choose your model has hyperparameters, like the layer size. The choose your loss has hyperparameters, like what type of regularization. And the choose your optimization has hyperparameters. So it's good to keep that in mind. And you're just going to get this big mess of hyperparameters that may interact with each other. There's another question in the lab where you think about that. And yeah. Controlling the fundamental trade-off, regularization. There's some weird names. So weight decay is just the name that people use for L2 regularization when they're talking about neural networks. Go figure. So there's some terminology to kind of work through. So batch normalization is, I don't know, few years ago, popular thing. I mentioned dropout. So these are things that, yeah, we just don't have time to go into detail for all of them, but if you're interested, I encourage you to learn about them. And in reality, when you're using neural networks, you will need to familiarize yourself with all these hyperparameters and put your fundamental trade-off hat on and think about these things, what's going to cause overfitting, what's going to cause underfitting. And at the end of the day, you may just do an automated hyperparameter search, which I think you did in 573, where you maybe just have 12 hyperparameters and you're just kind of, for example, doing random search, but also maybe something more sophisticated. Questions or comments? Sri?
Do we have to worry about feature scaling when using neural networks?
Yeah, do we have to worry about feature scaling when using neural networks? So I would say just, it's a good idea. You can do the standard scalar or whatever it's called in scikit-learn. Yeah, it's generally a good thing to do. So, yes. Okay, this backpropagation, maybe many of you have heard the term, or maybe not, sometimes also called backprop. We do not have time to go into it. It is optional. The last question on this week's lab is this optional question that is a very large amount of work, but if you're super interested in neural networks, then you might want to take it on. It's basically like implement a simple neural network from scratch. Backpropagation sounds like this fancy thing and it's famous or whatever, but it's not really that big of a deal. It's just when you're taking the gradient, like for example, the logistic regression loss you had earlier in this course, I gave you the logistic regression loss gradient. It's still a pain to take that gradient with pen and paper, but at the end of the day, you're just taking a bunch of derivatives. With the neural network, it's a bit more of a pain because you have all these layers, and so you have all these derivatives of the loss with respect to the things in this layer, and respect to things in that layer, and respect to things in that layer. And the 1-minute summary is just like in the algorithms and data structures course where we talked about dynamic programming, memoization, caching, like store the result instead of computing it over and over again a million times. All backpropagation is that. Store the result so you don't compute it over and over again a million times when taking the gradient in neural networks. Because basically, if you want to compute the derivative with respect to the weights in layer 1, you're going to be like chaining yourself, applying the chain rule literally through all those layers. And so you may just, and if you naively do it, you'll just waste a lot of computation. So that's all there is to it. And we don't have time to say, OK, these things multiplied, it's just the chain rule. But we don't have time to go into it. So let's move on. Yeah, depending on your interest level in neural networks and how much you end up using them in the future, you may want to go into more depth in those things. OK, the last 9 minutes that we have left. Hopefully there was some stuff about convolutions in the video. OK, at least one person said yes. So I was just sort of stealing some time from next week. So next week is going to be all about convolutional neural networks. And as a kind of prereq for talking about convolutional neural networks, I wanted to talk about convolutions. So that was in the video for today. I had some true or false questions, but we talked about the quiz longer than I expected, so we can't do those today. So let me just give you the 8-minute summary of the convolution stuff, and then all next week, but especially on the first lecture on Monday, we'll be building on that. And the convolutional neural networks are really fun because they work well for structured data, like images and audio and all kinds of stuff like that, videos. Right, oh, I won't steal my own thunder. OK. What is a convolution? So a convolution is a mathematical operation. It comes a lot from the signal processing and sort of communications world. I don't know if we have any like electrical engineers here or anything, but some of you may have seen it before in physics or math or somewhere. A few things to say about convolutions. So I'm assuming you've looked at the video, but they're an operation that you do to two things, and usually call those two things a signal and a filter, but those are basically just words. Like multiplication, if I do, I don't know, 5 times 3, multiplication is just an operation we do between a number and another number, or maybe between a vector and a number, or maybe between a matrix and a matrix, right? So convolution is an operation that you do between structured data. So, for example, a time series, right? In a time series, you have the temperature today, the temperature tomorrow, the temperature the next day. There's an order to your data, which is something we haven't done so much of until now. Or in an image, right? If you have an image, it's a two-dimensional image, and you can't just reshuffle where all the pixels are. That's going to mess up the image. So convolutions operate on those types of structured signals, as we call them, one-dimensional, two-dimensional, three-dimensional, etc. And there's a specific definition that's gone through in the video of what a convolution actually does. But it's basically an operation for transforming one of these signals into another one. So in fact, in the programming course, this is a while ago, but there was that stock market thing, and you had to apply a smoothing operation. That stock market thing was a time series, right? It was the stock price from now to then, and then you did that smoothing thing. That's actually an example of a convolution, and you probably had that in the video where there was a smoothing operation. But those are the type of operations that can be expressed as convolutions. This is, again, this is a very high level, like, video recap type thing. Sometimes people write it with a star. And, geez, we're in this very awkward situation with 5 minutes left and these true or false questions that I had. I actually liked what we did during the snow day with the true or false questions on Slack. So I'll do the same thing with these because we really don't have time to do them, and we could try to do those over the next, say, day. Are there any general questions before we wrap up, or should we just end 5 minutes early? No one dares raise their hand because everyone will be mad at them. Okay, let's end. Let's end 5 minutes early, and I'll see you next week.